There's two types of fluid flow. The first type is smooth. So when the flow of a fluid is smooth, we call it streamline or laminar flow. And what this looks like is something like this if you Google diagrams. And each particle of the fluid follows a smooth path. These paths do not cross, and the smooth path is called a streamline. When the speed gets too high, when it crosses a certain threshold, the flow becomes turbulent. This is the second type of flow. Imagine there's an object here, and there's air flying around it. Turbulence would look like this. It'd be these little circular, chaotic, whirlpool type movements. And they're called eddy currents. So eddy like that, eddy currents. Eddy currents absorb a lot of energy, and the viscosity is much greater. And viscosity is a special type of friction in fluids. It is present in laminar flow, but it's much greater in turbulent flow. This is the main point of this video. It's the equation of continuity. And this equation, at its simplest, is area times velocity is equal to area times velocity at a later point. It's like conservation, and I'm going to derive this. If you don't care and you only want to solve problems, skip ahead. But where does this equation come from? Let's set this in the corner because that's our goal. Imagine a tube with two openings, and at one point it gets thinner. This here is area 2. This opening is area 1. When it enters, it's traveling at a certain velocity. And the length it travels in the time interval t is equal to L1. When it crosses through area 2, the velocity we'll call v2. And the length this travels is L2. In the same time interval, because the speed of the fluid changes when the diameter changes. It's smaller here, so speed went up. Even though the amount of fluid coming in is constant, there's something called the mass flow rate. It's the rate that mass flows. Who would have thought? And it's given by change in mass over change in time. The amount of volume passing point 1 in this time interval t is area times the length. So area 1 times length 1. And mass can be given with density times volume. Of course, we can go further. Volume is A times L, like we just discussed. And here, look, length over time. What's length over time? That is average velocity. So that's how fast it's going in. So we just get this. Density times area times velocity. That is the mass flow rate. Let me write that out. That's how important it is. That is the mass flow rate for stuff flowing through point 1. At point 2, it's the same thing. Density, area, velocity, just for the second part. And since we're assuming there's no weird fluid coming in externally through the sides, it's just this. You enter through here and you keep flowing through here. That means the mass flow rate through point 1 and point 2 are equal. So mass flow rate of 1, mass flow rate of 2, it's equal. And here's the variation. This right here, this is the equation of continuity. And it's basically energy conservation, but for mass. And here's how we get our original goal. If the density is constant, so it's the same across both points, then we can cancel it out. And here, that's the equation we were trying to derive. This is a variation. All three, they all work. So let's see it in action. Here's a problem. You're a shower engineer, and what you're trying to design is a shower head feature that splits the water into ultra-fine mist for this spa effect. Let's draw a diagram of what's going to happen in this problem. So this is the pipe to your water. This is the shower head. The diameter of the pipe is 1 centimeter. And water enters at 0.5 meters per second. They exit these tiny holes, and each of these tiny holes are 0.1 millimeters wide. And they exit at the speed of 2.5 meters per second. how many mist jets, how many holes in the shower head is required, because the mass that's flowing through is constant. So there's a specific amount of holes that we're going to need. Let's have a look. On the free cheat sheet in the description, I have all the equations we're going to use for this problem. First one being the conservation of flow, aka the equation of continuity. It says total flow in is the same as the total flow out. And the equation is this. But on the right hand side, we're going to multiply this by n. What's n? N is the number of holes, because our flow, instead of one clean pipe like this, it's getting split up into all of these mini holes. How the flow is split. And that's what we're looking for. We're looking for the number of holes. What do we know? We don't know the area. We do know this velocity is 0.5. We don't know the area on the way out, and we know the velocity on the way out is 2.5. All you have to do for the areas is, it's a circle, right? They're circles. So you use pi r squared. And pi r squared, you plug in the areas, respectively 0.05, an even smaller version of 0.5. And when you find the area with your pi formula, for the output side, it's 7.85 times 10 to the power of -9 meters squared. For the input side, it's 0.0000785. Similar values, but this one's way smaller. We're dealing with very small numbers, of course, so it's a bit hard to imagine. Let's just let the math do the work. So, solve for n, and you get n equals the input flow divided by the output flow. Let's plug in our 4 values. And when you put it into a calculator, you get 2,000. So you need 2,000 holes in your shower head to make this cool mist effect when you know your flow rates and your tube sizes. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.